Okay. In order to understand mass spectrometer, you should know these four things. First is ionization. Ionization means conversion of element into ions. Okay, so when a sample is injected in the mass spectrometer, first of all, it gets ionized. Ionized means it loses electron and becomes positively charged. Okay, so when it becomes positively charged, so definitely it will be called as ions. Okay, so the first step in mass spectrometer is ionization. And there are two types of ionization: electrospray ionization and electron impact ionization. Okay, what is electrospray ionization? Okay, electrospray ionization looks like this. Can you see whiteboard?
Yeah, I can see it.
Okay, basically, let's say this is mass spectrometer instrument. It has different parts. Okay, so this is a sample compartment from where sample is injected. Sample is injected. Okay, and the first chamber is called as ionization chamber. This is ionization chamber where electrons are bombarded. Okay, electrons are bombarded on the sample, so sample gets ionized. Okay, so let's say these are sample molecules that move toward the ionization chamber. So some electrons are bombarded on it. So, but ionization can take place by two methods: electrospray ionization and the other method is electron impact ionization. Electrospray ionization is, in this method, the sample is dissolved in a solvent and pushed through a small nozzle at high pressure. Then a high voltage is applied to it, causing each particle to gain a proton, and the solvent is then removed, leaving a gas made up of positive ion. So basically, electron spray ionization is like sample is injected in the form of a tube, or you can say this is a nozzle. Okay, and sample is sprayed like this. It is in the form of droplets. Now the sample is in the form of droplets. Then a high voltage current is applied. Let's say this ionization chamber is connected with a battery that provides voltage. And due to this voltage, these droplets of sample ion will take hydrogen ion, and all of these will become positively charged. When they become positively charged, then definitely now these are called as ionized particles. Sample is ionized. Now it is in the form of ionized particles.
Right. Okay.
Got it? This is first method, and this method is called as, in which it is sprayed in the form of droplet. This is called as electrospray ionization.
Right. Okay.
Yeah. Then another method is electron impact ionization. This ionization chamber can be different in different mass spectrometers. In this one, the sample is vaporized and an electron gun is used to fire high energy electron at it. This knocks off one electron and so that it becomes positively charged. For example, in electron impact ionization, okay, yeah, let's say this is mass spectrometer. If ionization chamber contains electron impact ionization, then when the sample is injected, in this case, sample should be in vaporized state, or you can say vapor state. Okay, sample should be vaporized first, and then these vaporized samples are now placed in ionization chamber. Then through an electron gun, over here, there will be an electron gun. or you can say anything that can provide electron. It can be metal filament or anything that can provide electron. So when particles are present over here, the sample particles are present in the ionization chamber, then electron gun supplies electrons to these sample particles. As a result, these electrons, or you can say these sample particles, will eject one electron. Okay, one electron is knock off from sample. So when the sample particle lose electron, after losing electron, we know that when an atom loses electron, when a sample loses electron, it will become positively charged, right?
Yeah.
It will become
Yeah.
positively charged part. So the in both of these ionization techniques, main purpose is to ionize the sample and mostly in positively charged state. Okay, we will ionize and make them positively charged. So, but the method is different. In first one, a sample was in the form of droplets, and then through voltage, it is converted into positively charged. While in electron impact ionization, sample was in the form of vapor state, and then electron gun supplies electrons so that it knocks off the electrons from the sample. As a result, sample becomes positively charged. Got it? Any question from ionization?
Um,
Okay.
so
Mhm. Yeah, can you tell me what
how
do you understand by electron impact and electron electrospray ionization?
so you said that the sample is in the form of droplets.
Mm-hmm.
So um when the sample is injected through nozzle, then it comes in the ionization chamber, and that's
Mm-hmm.
where the electrons are bombarded, so the sample gets ionized.
Very good.
And then,
Uh, And this is electrospray ionization. Sorry, this is electron impact ionization. When electrons are bombarded on it, that's electron impact. Okay, but
right,
in this one, in electrospray, it is different. In electrospray ionization, there is no electron gun. Over here, voltage is applied by electricity, basically. Okay, so you have to mention that in electrospray ionization, voltage is applied, and this voltage causes the electrons to move out. As a result, sample becomes positively charged. Got it? So there
right,
is a
okay,
difference between electrospray and electron impact. The one that you were telling, that was electron impact. Okay.
right, okay,
Next part. Next part is acceleration. Acceleration is those positively charged ions that are formed in ionization chambers. Now they are accelerated by an electric field. Okay. The lighter ion experience greater acceleration and the heavier one. Okay. Basically, now after ionization chamber, there are two plates present. These are called as accelerating plates.
right,
Accelerating,
okay,
yes. And accelerating plates have negative charge. They have they are negatively charged, and these are connected with an electric field. Electric field, or you can say voltage is applied. So definitely voltage is causing an electric field. It is providing electric field, right? So the positively charged ions that were formed in ionization chamber, then they are attracted toward accelerating plates. You know, negative attracts positive, right? So these positive ions, due to opposite charge, they are attracted toward accelerating plates, correct? And then they move from one plate to the next as well due to charge difference. Positive charge particles will move toward the accelerating plate, okay? And obviously some of the particles will be smaller, some particles are heavier ones, so lighter particles move faster. Okay, you have to note it down. Lighter particles accelerate faster, okay, while heavier ones move slowly toward the accelerating plate. Okay, so it depends on the masses as well, because obviously the main purpose of mass spectrometer is to measure the mass. So definitely there will be some processes that are different in different masses, right? So lighter particles accelerate faster while heavier ones move slowly. Okay, in both of these basically types of ionization chamber, the next thing will be the same. The accelerating plates are negatively charged, so that's why positive ion can easily move toward those accelerating plates, depending on their masses. Got it?
Right. Okay.
Yes.
Yeah.
Next is ion drift. The ions enter a region with no electric field. They drift through at the same speed as they left the electric field, so the lighter ones will be drifting at higher speeds. Okay, and then there is detection. So over here you can see this was ionization chamber. Then these two are accelerating plates that are provided with electric field. And after accelerating plates, there is no electric field. In this area, these particles will move. Okay, and then again heavier one and lighter ones. So then you can see in our diagram, after accelerating plate, the next part is over here. You can see this is detector. Detector. Between accelerating plate and detector, there is a region where there is no electric field. Okay, so after accelerating plates, the ions will move, the positively charged ions will move toward the detector. Okay, again now there is no electric field, but detector plate is also negatively charged, so that's why positively charged particles are easily accelerated toward the detector as well. So when these ions move from accelerating plate to detector, this process is called as ion drift. This process is called as ion drift. Correct? And then they are detected or the detector depending on their masses. Detector will detect like how much similar type of molecules are there, so it will detect it. Okay, and it will provide the relative abundance and the type of isotope or type of sample.
Right. Okay.
Correct? Any question?
Wait, so then if the lighter ions travel like
Hmm.
faster,
Uh-huh.
does that mean the detector detects them more quicker then?
Yes, exactly. That's right. They reach the detector faster and earlier than heavier.
Right. Okay.
Hmm. Any other question?
Um, and
Okay. Okay. Next part is after detection. Okay, this is called as ion detector. So basically, we can say that there are three phenomena that are taking place in mass spectrometer. First, ionization, and we discussed there are two types of ionization. Over here, there's positively charged ions are formed. Then it moves toward the accelerating plates. Accelerating plates are negatively charged. That's why positively charged particles are attracted by it. And then after that, between acceleration and the ion detector, there is a region where particles move toward the ion detector, right? Hmm. Then detector detects it and makes a spectrum. Spectrum. Okay. The results. Okay. It appears in this form. Okay. This mass spectrum looks like this. On y-axis there will be percentage abundance of a sample, of a fragment, in other words, and on x-axis there will be mass to charge ratio. Okay. Charge of mostly ions would be plus 1. Okay, charge of most ions is plus 1. As we said, they become positively charged, so definitely they will lose, mostly will lose only one electron. So that's why they have plus 1 charge. Okay, so
right.
a
Okay.
mass spectrum is a type of charge provided by a mass spectrometer. It shows information about the sample that was passed through the mass spectrum. Over here, percentage abundance is shown and mass to charge ratio. So if a element has 4 isotopes, so you'll see the number of peaks will be 4, because you know that there are different masses. Isotopes have different masses. So isotopes, hmm, number of isotopes will be equal to number of peaks. So for example, in paper, this mass spectrum is given and they ask you like how many isotopes this element has. So you'll say that you'll just count the number of peaks. So there are four peaks. So you'll say that okay, four peaks means four isotopes.
Okay.
And the height of peak describes the relative abundance of that isotope. For example, the mass spectrum produced when a sample of lithium is passed through a mass spectrum. Okay, so you can see there are two peaks, which means that lithium has two isotopes. Okay, and what's the mass of both of these? So you can see that one has 6 mass and the other one has 7. Okay, it's a mass to charge ratio. So basically charge is also plus 1. So 6 divided by 1 is also 6. Right. Similarly, 7 divided by 1 is also 7. So you can say that this is a mass. Mass of one lithium is 6, other one is 7. And the relative abundance of lithium isotope having 6 mass is 7.6. It is 7.6% in nature, and this one is 92.4% in nature. Okay. The purpose of mass spectrum is to figure out the mass of isotope and the relative abundance. Because if we know both of these, then we can figure out the relative atomic mass of element. If you remember the formula for relative atomic mass is mass of isotope 1 times by relative abundance of isotope 1 bracket plus mass of isotope 2 times by relative abundance of isotope 2 divided by 100, right? So this is
Yeah.
the formula. If you remember, we studied this one in last lesson as well. Do you remember?
Yeah.
Rafi, do you remember this formula?
Yeah. I remember.
Okay, okay, then good. Then we can just put the values. Relative atomic mass AR is equals to 6 times its relative abundance 7.6 bracket plus 7 times 92.4, right, divided by 100. Calculate it.
So it is 6.924.
6.924. So this is the exact relative atomic mass of lithium. Very good. Perfect. Okay, there is a practice question. You will solve this one. The mass of spectrum for a sample of copper is shown below. Okay. How many isotopes of copper were in the sample? This mass spectrum is given. Can you tell me how many isotopes are there?
So two, because it's two peaks.
Very good. Perfect. Two peaks, two isotopes. Okay. Then give the relative isotopic mass of each isotope. What's the mass of each isotope?
Each isotope. 60 and 65.
65, 63 and 65. Correct. Okay. Give the relative isotopic abundance of each isotope.
69.1 and 30.9. Oh no, no, no.
69.1.
Oh, is that right?
Uh-huh.
Oh, okay.
Yeah,
Yeah.
it is 69.1 and 30.9. That's right.
Okay.
Okay. Can you tell me its the relative atomic mass? Its relative
Yeah.
atomic.
So
Mhm.
uh 69.1 times 63, add 30.9 times what is he doing? 65
Correct.
over 100. So 69.1 times 63 at 30.9 times 5. over 100. So that's 63.618.
Correct. Very good. That's right. Very good. Similarly, you can identify elements on the basis of their mass. Obviously, when you determine their relative atomic mass, then you can analyze the elements as well. Like magnesium has three isotopes with percentage abundances shown in the table. If a sample being analyzed contains magnesium, this isotopic distribution will show up in the mass spectrum. So if you get this ratio, like 79, 10, and 11, and their masses are differing in 1, like 24, 25, 26, then definitely the compound contains magnesium element. Okay, so by using the ratios of percentage abundance and their masses, we can identify the elements as well. Okay, this is
Okay.
also a use of mass spectrum. Okay, table below shows the relative abundance of the stable isotopes of three elements. The mass spectrum for a single sample of unknown element is shown on the right. For each element listed in the table above, explain why the mass spectrum suggests that unknown substance is unlikely to be that element. Because for magnesium, in this mass spectrum, you can see there are total three peaks shown, right? Three peaks means this element has three isotopes, right? And its
Yeah.
relative abundance of these three isotopes is around 85. This one is 2%, and this one is around 10%, right? So this relative abundance is not matching with any of them. Okay, magnesium has 79, 10, and 11. So this relative abundance is not corresponding to this spectrum. So it cannot be magnesium. Similarly, silicon has isotope 92.2, right? But over here it's 85 around something or 90. So obviously 4.7 and 3.1, it is not corresponding. And indium has only two isotopes, so it cannot be this element. Okay, so it means that this spectrum belongs to any other element but not these three.
Right.
Clear?
Okay.
Yes. So this was all about mass spectrum.